Hello, and welcome to the next exciting installment of digital design. Now we're going to do something kind of magical. How can we build logic gates from these transistors? So let's start out with a NOT gate. Remember, when A is 0, the output should be 1. When the input is 1, the output should be 0. We can build the NOT gate out of a single NMOS transistor and a single PMOS. The NMOS is connected between the output and ground. The PMOS is connected between the output and power. When A is 0, the PMOS transistor is on, the NMOS transistor is off, so there's a path from power to the output. There's no path from ground to the output, so the output is 1. On the other hand, if A is 1, now the PMOS is off, the NMOS turns on, there's a path from the output to ground, there's no path from the output to power, so the output is low. So sure enough, the output is the opposite of the input, and we have a NOT gate, built out of only 2 transistors. Next, let's look at a NAND gate. For a NAND gate, we'll put 2 NMOS transistors in series between the output and ground. We'll put 2 PMOS transistors in parallel between the output and ground. And remember, the NAND gate is opposite of AND, so it should produce a 0 output only when both inputs are true. So if A and B are both 0, both PMOS transistors are on, both NMOS are off, so there's no path from Y to ground through the NMOS. There's a path from Y to power through either PMOS. In fact, there are 2 paths through both of the parallel PMOS, so Y definitely becomes 1. Let's say A is 0 and B is 1. When A is 0, P1 is still on, P2 is off. N1 is off, and N2 is on. So there's a path through P1 from Y to power. There's no path through P2, but it doesn't matter. There's some way for power to get to Y. So Y will become 1. There's no path from Y to ground, because even though ground could get through N2, it gets blocked by N1, so there's no connection from Y to ground. If A is 1 and B is 0, we're similar. P1 is off, P2 is on, N1 is on, N2 is off. There's a path from Y to power through P2. There's no path from Y to ground because one of the 2 series transistors is cut off. So again, the output is true. Finally, if A and B are both true, P1 is off, and P2 is also off. N1 is on, N2 is off. Now there's no path from Y to power, because both PMOS are off. There's a path from Y to ground through the 2 NMOS transistors in series, so the output goes low, and sure enough, we've built a NAND gate. So in general, we build logic gates with a network of NMOS transistors between the output and ground, a network of PMOS between the output and power. Suppose we wanted to build a 3-input NOR gate. A NOR produces a true output only when all of the inputs are low. So to build this with transistors, we'd like to have a path to the power only when all of the inputs are low. So we need PMOS transistors, 3 PMOS transistors in series. only when all of these inputs are low should the output pull high. If any of the inputs are true, we want the output to pull low, so we'll build 3 NMOS in parallel to ground, A, B, and C. If any of the inputs are true, the output will go to 0. So here's our 3-input NOR. Let's suppose we wanted to build a 2-input AND gate. The problem we have is the NMOS pull down, so as we have more ones on the input, the output wants to pull down. If we have more zeros on the input, the output wants to pull up through the PMOS. So we can't directly build a non-inverting gate like an AND in CMOS. However, we can build a NAND and we can build a NOT. So we can build our AND gate as a NAND followed by a NOT to do an AND. Remember, our NAND gate has 2 PMOS in parallel and 2 NMOS in series. Our NOT gate just had a single NMOS and a single PMOS. And so here's our 2-input AND. So another issue happens if we wanted to build a good switch. Remember that NMOS pass 1s poorly, PMOS pass 0s poorly. If we wanted to build a switch that could pass both 0s and 1s, we need both flavors of transistors working together. And we call that a transmission gate. So let's say we take an NMOS and a PMOS and connect them together between input A and output B. We'll connect an enable signal EN to the NMOS and its complement to the PMOS. When enable is 1, the switch is on. Enable bar is 0, and both the NMOS and the PMOS are turned on, and input A connects to output B. When enable is 0, the NMOS is off, enable bar is 1, so the PMOS is off, and there's no path from A to B through either NMOS or PMOS, so we say the switch is off. So one of the very important figures in semiconductors is Gordon Moore. Moore co-founded Intel in 1968 with Robert Noyce, and early on he took a look at the number of transistors on chips, and he found that it was doubling every year as of 1965. He plotted that on a semi-logarithmic plot and predicted that if that continued, we'd have exponential growth in the number of transistors on a chip, and amazing things would happen. So that growth doubling every year slowed down a little bit, but since 1975, the number of transistors on a chip has doubled approximately every 2 years. And so we've gone from 2 transistors on a chip in the 60s up to hundreds in the 70s, and now billions today. And this is known as Moore's Law, that the number of transistors you can get on a chip is increasing exponentially. Some corollaries of that is that the transistors are getting smaller. They also become faster and consume less power, and they're cheaper. So we have this vicarious cycle that is making chips better and better. So here's a historic plot of some Intel processors. The 4004 was the first microprocessor ever produced. Came out around 1971 with about 2,000 transistors on it. And nowadays, by 2006, we had over 100,000 transistors, Now we have close to 10 billion transistors on a chip in 2020. And so we've been very steady on this exponential growth over 5 decades, which is incredible. There's nothing else I can think of in the history of technology that has increased at a dramatic exponential for 5 decades. Robert Kringley had a famous quote that if an automobile had followed the same development cycle as Moore's Law, a Rolls-Royce today would cost $100, would get 1,000,000 miles to the gallon, and like computers, would explode once a year.